experimental data that you just get as they are, and perhaps you don't have super many degrees of freedom to adjust the experiment. So there is this whole workflow of pre-processing, pre-formatting the data, feeding them into the model, and then interpreting the data from the model in the real time, perhaps in some feedback loop, so it can actually benefit to your experiment. So this is kind of a broad question that is a bit separate from just learning about machine learning models, but it's about learning how to embed them into a bigger picture experimental workflow. So that's what we are going to do today. Before we do that, I just want to do a quick lightning round quiz. So you warm up to think about a little bit about the things that we were thinking yesterday. I am just gonna ask very quick questions, and I'm just like looking for like a few words answer, nothing elaborate. And yeah, we do it for a couple of minutes until I run out of questions. So what is a convolutional filter? Anyone wants to tell me? Come on, these are simple. I know you know it. So there is one raised hand in the back.
So it's the collection of weights that you use in a convolutional neural network, and it's kind of exactly like the filter that you would use in an image processing. So it's a set of weights that you move across the image, and they kind of give you the output for certain regions of an image.
Perfect answer. Thank you. Next question. What is the reason to have such convolutional filters? Why couldn't you just have dense feed-forward layers? Can you tell me one difference? We have a raised hand over here. Grace.
Yeah, because you want to make use of the locality of your information and the local correlations.
Perfect. Great answer. Next question. What is a regularization and why is it needed?
So it's a technique used to avoid overfitting, and it's well, takes different forms. One of them is a dropout dimension. So you forget links of your neural network for training to avoid overfitting.
Very good. This leads me to a follow-up questions. What's an overfitting?
When your model starts to learn
to fit the noise of the data.
Okay. Follow up. Now I will torture you a little bit. How can you tell that this is what happened?
Because when you try on validation data, it doesn't generalize well, and you have a low error on the training data, but as soon as you put in new data or unseen data to the training set, it doesn't generalize.
Great. Okay. Next question. What's Hamiltonian learning and why would you want to do that? We talk about it for like over an hour, so I'm sure you know. So maybe just the first half, what's the Hamiltonian learning? Can anyone summarize it with like a one sentence for the rest of us? I mean, the next question is about the Juan stuff, so this is still easy. Okay, please.
Right, let me liberate you. So it's trying to learn the parameters of a Hamiltonian from data, let's say experimental measurements, right?
And why is that interesting or useful thing to do?
Well, I have a similar problem that I want to solve in the next half a year. No, it's because well, let's say they have a quantum simulator. And they want to prove that they can simulate reliably some stuff. They want to first be able to show what is the Hamiltonian that they're actually simulating, to be able to compare with the analytical prediction or so on.
Perfect. It's just this thing that when you have only access to the data and you want to reconstruct your model, learning the physics is the same thing as learning the Hamiltonian, i.e. Hamiltonian learning. Next question, what's a POVM? Do you have a hand over here?
It's short for positive operated valued measures, and you can use it to kind of translate your density matrix into a probabilistic framework, or at least that's what we use it for.
Yeah, that's a true statement. Follow up. What's a key difference between projective measurement and a POVM? What's the one thing that separates the two? Would you know?
So I know for sure that the POVMs allow you to reconstruct the entire quantum state, and projective measurements usually only have spin up and spin down. So reconstructing a density matrix. So it's not informationally complete, that's my point.
Interesting. That's very good. We had one more raised hand. Did you have a follow-up? Or you wanted to say the same?
That the projective measurement is necessarily orthogonal and the POVM isn't.
Perfect. That's what I wanted to hear, because thinking about these reconstructions can be a little bit abstract, but it's super, if you think about it for 5 minutes, you will realize that it's super intimately related to this informational completeness you were mentioning. So projective measurements, they always have to be orthogonal to each other, but the POVMs, they just have to add up to 1, but the orthogonality is not needed. So it gives you much more flexibility in monitoring your state. And maybe one last question about what you were learning yesterday. Quick summary, what is the difference between, so Juan was showing you RNNs. How was that different from the neural networks we were looking at in my lectures? What's the one thing that the RNNs have? We have a raised hand over there.
The RNNs have a hidden state that gets updated every time step.
Perfect. So that was this recurrent feature that you have one extra output that the network keeps feeding to itself. Okay, I think that's enough. So let's move on to. Oh shoot. I see you restarted the Zoom. Oh, okay. This will take me a second because I need to find the link again. In the meantime, I want you to think about, if I ask you what are two-dimensional materials, is this something that means anything to you? Now my Zoom crashed again. Interesting. Okay, let me try again. Okay, there we go. The two-dimensional materials, does that mean anything? Can someone kick us off to tell us what it is? We have a raised hand over there.
Yeah, so two-dimensional materials, of course, like don't truly exist in a three-dimensional world, but you just call them two-dimensional if they are like comparatively big to all like quantum length scales in 2 dimensions, and small in comparison to some quantum length scales in 1 dimension.
And that 1 dimension that is small, can you give us order of magnitude or number of constituents? That what does it mean, small?
Well, as I said, it depends on the length scales of your system. Usually, like, you know, if it's like in the order of the dominating length scale of your system, I would say it is small. But usually this will be like several angstrom, I think, so a couple of atoms.
Yeah, a few atoms. That's perfect. Thank you. Anyone knows an example of such a two-dimensional material? There is one very famous one. There's a Nobel Prize about it and everything.
The monolayer graphene, so single atoms in a honeycomb, single atoms thin, and in a honeycomb lattice in 2 dimensions?
Perfect example. Great. Now, maybe this is a hard question. Anyone knows any other material that is not graphene, but is also 2-dimensional? We have a raised hand over there, Kayudi.
Hexagonal boron nitride, which I think is used for quantum emitters.
Perfect. This happens to be background of my picture here, so that was a perfect answer. One last question: why is it so interesting to have this thin layer material? So I have a 3-dimensional. I have the same things existing also in 3 dimensions. Why cannot I just take the 3-dimensional? Why are people so obsessed with this thin layer? Is there some difference between this? Why is it that like this thin materials, like why is it that the discovery of graphene was such a meaningful game changer for us?
I would come back to the length scales. So basically, like if you have a 2-dimensional material, you know that like in 2 dimensions, it will usually behave like pretty classical, but in 1 dimension, it will behave very, very quantum mechanical. So it will therefore probably behave very different from a true 3D material.
Yeah, that's a great answer. And that's exactly, basically, if you peel just this few atom layer of your material, it turns out that you can have a strikingly different properties. And then the next funny thing you can do, that you can literally play making a sandwich with your materials, because you have just these few atoms layers on top of each other. So you can like hyper engineer your band structure by sandwiching them. And this is how people are building quantum devices nowadays. And that's why this discovery was so game-changing, because a lot of quantum devices are built using this band engineering, basically. This is very advanced condensed matter physics that I'm not going to talk about today. I want to talk about something much more easy, and that's something that is related to creating these devices from these materials. So, as I was just saying, you have these materials that are key constituents of the devices. So you want to find the correct pieces of the materials. They call them flakes. Those are the colorful pieces you see on the background. Here I have the picture of hexagonal boron nitride. So hexagonal boron nitride is amazing because it's a great insulator, but at the same time, it has a hexagonal lattice. So people really like to use it to sandwich the graphene layers together so they can build a graphene-based devices. So this is just some examples of like, here you see like a different experiments with different names of these materials that are very thin, and how would you sandwich them. This is just for your reference later if you want to look up some interesting things. Now, the challenge is this. Creating this 2-dimensional materials is literally done by mechanical exfoliation. You literally mechanically peel off the layer of your material. Then you deposit it on some substrate. And this is how it looks in practice. On the right-hand side of the picture here, you see a glove box that inside is filled with some like rare gas, so there would be no impurities sitting on the sample. Somebody puts on these huge gloves, sits in front of the microscope, and searches through this kind of, these are examples on the left, like pictures that the microscope would take, and just keeps manually scanning through the sample, looking for the flake that is a good one. And so it happens that the flake that is a good one is a really rare thing that depends on a lot of different parameters, like a color, thickness, presence of cracks, and so on. And what's worse is that the microscope has a background lighting, and the lenses are different in different microscopes, and the substrate you put it on differs in color. So you cannot even say, I see this RGB color and that's the correct flake for me, because based on all these other outside conditions, you have this may really colorfully differ. And for example, for this hexagonal boron nitride, there is a broad spectrum of colors that could potentially be a good flake. But then what happens is that experts who are late in their PhD or in their postdoc, instead of doing useful work, are doing this. So this is one of those examples that is like not super physically deep, but is ripe for automation, because maybe you don't want to spend half of your PhD doing this. So let me explain this diversity I am talking about on the example of this hexagonal boron nitride I have in the background. So for example, this flake would be potentially good. The light green tells you that it's relatively thin, so it could be a good device flake. This one could be good to substrate flake, but you see perhaps that there is a crack in it along this line, and that's really bad. That could potentially harm your device. These two could be good, but they are accidentally stuck to each other, and if you try to separate them, you are just going to break everything. So that would be a waste of time, and so on and so forth. So there is a lot of diversity. So you see that this kind of brings you back to this distinguishing dogs from cats, or Star Wars and Star Trek characters, right? Because the set of the things that you need to distinguish is really, really different. So here is just some examples on these 3 images of how the good flakes that were found by a human operator looks like. And what we really wanted was to really automate this process end to end, so nobody has to sit there and do this. So first thing we did was to just make the microscope move automatically. These commercial microscopes, they have a drivers that you can get from the manufacturer. So basically what you just need to do is to write the API for the manual arm to communicate with the microscope and move it around. So here on the right hand side so you see like a real size of the wafers that you would be scanning. And again, on the left hand side, you have some examples of the images. So the first thing is for the microscope to move and also zoom correctly. Again, be aware what we heard from over there. There is really like very subtle height differences, but if you are exfoliating, you are also going to exfoliate big pieces of the material. So the microscope really needs to learn to zoom on the correct thing and not be distracted by some bumps that have much thicker layers around it. Second thing we did is that we made our experimental team in the Klaus Entlin and Thomas Ihn group at ETH label. To make this really, really simple for them, they created just like a very simple like graphical interface to do it, which is the picture that you see here on the left, where basically these pictures from the microscope are coming, and as they are coming, there is a person sitting next to them, and when they see a flag that could be a good flag, they click, and the red cross is translated into the data file that gives you coordinates of that flake on the coordinates of that flake on the picture, and then also translates it into the coordinates onto the whole wafer. So just by clicking, you do all of this, and you don't have to by yourself thinking about measuring these things. So we have these big pictures, and we have some labels. Now you can kind of already see that there is a lot of let's say dirt, but also some of this dirt could be useful flakes in these pictures. So at the beginning for us was sort of this wasn't a super suitable task, also because we are limited in the amount of data for one of these algorithms that searches objects in a picture, because we have a lot of objects and the size of the good object that we are looking for really, really differs. So we did something different. We decided to make a pre-processing to really standardize the data. And basically you can just use a Python image library that does the following. You load each image as the data. That's the big one on the left. And then you just run some criterion, like you scan the data by some criterion, and based on that criterion, you cut out the smaller images. For us, we were looking at the standard deviation changing between the following points. So basically, we would distinguish a boundary of the flake, that something is happening. This is, of course, a method that is going to pick up absolutely everything. It's going to pick up the flakes, but it's also going to pick up a lot of useless things. But this is a way to just generate hundreds of thousands of squares like this, and some of them will have a useful flakes in the middle. Which of them will have the useful flakes in the middle? The ones that contain the flake that somebody clicked. So all we have to do is then to reference these squares. Again, when we are creating the squares, we need to like meticulously keep track of what is the coordinate of each square on the picture and on the wafer. And then all you have to do is cross-reference your squares and check if they contained the red cross in them. And if they contain the red cross, you are going to give a label 10, hot encoded, one hot encoded class, this is a good flake. And if they do not include the red cross that nobody clicked on, then it's a bad flake, right? So this was kind of a method to really use the human labeling, but really minimize the workflow and then create a standardized training set. Is this clear up to this point? Okay, I see a lot of people nodding. I don't see any questions. There is one question.
But was it a method of looking for single flakes or multiple flakes or any flakes which can be useful in building a device?
That's a great question. So this was, so in this specific material, and I'm going to show that for different materials, this is not the case always, but for this HBN has a wide range of uses. And since all these experimental teams share the same glove box, we kind of wanted to develop a method that produces samples for the HBN specifically that are good for everyone. So the samples they were looking for were anything anyone from the different teams thinks it's good. And for some people, this was this big yellow thicker flakes. And for some people, this was smaller green flakes. Okay, I see. But you wanted a follow-up, I think.
So that was labeling the interesting flakes, I would say.
That was labeling, yeah, whatever's interesting, label it, type of labeling, yeah. We have urgent, how do you choose the multiple flakes when there are few on the square? This is absolutely wonderful question. So I'm going to show you this this later in detail, but basically we are building a software that is for the experimentalists to use. So sometimes indeed it happens that like there is a few good flakes on the same sample, or there is a few flakes on the sample and only one of them is good. And then the person who is looking at the post-processed flakes and is about to zoom the microscope there and lift it needs to know which one, right? Because indeed, like we were picking these squares such that we kind of had a good length scale estimate for how big the flake is. So I picked it in a way that at least for the big flake, I would really minimize the probability that there is going to be two of them. But for the very small flakes, this is not the case. And then you need to find the ways to solve it. And the simplest way to solve it is just to assume that the expert who does this will know. But we will reduce the amount of work for them radically. Maybe now this doesn't make super much sense, but I'm going to show on a very concrete flake example, just like in 10 minutes. I will remember to bring this up again. This is a great question.
Yeah, hi. From the way that you generate the data, it would seem that you have a lot more bad examples than good examples.
Yeah.
I know this can be a problem in classification tasks, so I
Yes.
was wondering if you take that into account and to what degree it is a problem.
This is excellent question, and this is the central point of why I'm giving this lecture. So I'm going to explain that in like 3 minutes from now. Do we have any more things we should discuss now? Looks like that's a no. So let me move on. And now immediately your question comes. Like this, they can scan a few wafers. I am going to generate around 100,000 flakes from that, except that good, the ones that are labeled as good, there is about 2,000. So first thing, now I am leaving the problems with the training for later. The first thing I will do is like that I will realize that this is a complete disaster either way, because the good examples are super rare. So a quick dirty thing you can do to enhance your good example in a training set is again to just use some basic tool. In our case, it was again just like a Python image library, but there are tons of other libraries for just like an image processing based on what you need. And we just did a mirroring and different rotations. And then we turned each flake into 6 flakes. Since they are so rare, so it, you know, it's not so likely you will overfit on a data set that has 6 good flakes that are all the same and 4 bad flakes in it. So this was an acceptable sort of thing to do, right? And now I wanna switch to the notebook here to actually show you now this problem that arose from doing this. That this representation really gives me, and I want to go over this very carefully because this is really a key problem. So you have this notebook 3. You will not be solving this notebook. I will just make it available for you in case you want to take a look. At the beginning, there is a bunch of just like a for loops that load the data properly and generate the labels based on how the files are named. And then you will get a data set, and this is not my real data set. This is just like a super tiny data set that made actually sense to upload to GitLab. That has about 6,000 something flakes, and has 300 for the evaluation, and the rest is for the training. So if you will run this notebook, you will see you will not get a good accuracy at all. This is just like for the sake of argument how these things work. So for all the reasons we were discussing yesterday, this is a problem where, of course, I am gonna need a convolutional layers, right? So I built a convolutional model here. Because of the diversity of the task, it will be no surprise to you that we actually needed a lot of layers and a lot of filters. So again, this is not super, this is something you can, if you get to this notebook, you can experiment with it. But basically, I kind of start, like a good practice with these things is that you start from a bigger kernel with less filters. And as you go deeper into the network, you make a smaller kernels and you can add more filters to kind of zero out on the small things. So I just built this completely standard thing. Then I compile the model and I will just get something like this. And it's like a million trainable parameters of. So I do this. I train for like 10 epochs. And when I plot loss and accuracy, so this is a loss for the training solid line and validation dashed line. So from what we learned yesterday and what we just discussed in the lightning recap, this is already a red flag for you, right? Because the validation curve does not follow the loss. And then you can also plot an accuracy and like, yeah, that's a disaster, right? So yeah, sorry, this is plotted very ugly way, but you see a bit the scale, right? So on a training set, you are going up onto 80%, but on a validation set, you basically have a coin toss. So what you can then do to understand what it happens is that you load your validation set. and you ask it for just a few flags to, sorry, validation set. You load extra test set, you just pick a few flags that you really know which image is which and you understand. You load it, you load your model and you evaluate it. And so I give it a few flags. I don't remember how many there is. I think it's around 20. And then for each flag, it tells me this is a bad flag with a probability 99.999%. And so I go and it thinks that every flag is a bad flag, except it's not true because every flag whose name ends with A is actually a good flag. But somehow it thinks it's a bad flag all the time and it didn't find any good flags. And this has to do with how these things were represented in the training set. Can someone explain what happened here? If you need me to go over the code again, I'm happy to. We have a raised hand over there.
Yeah, and the training set probably were much more bad flags than good flags. So it's a very easy local minimum optimization to just guess everything is a bad flag.
Exactly, exactly. That's exactly right. Like imagine someone gives you super tedious classification task, like finding a needle in the haystack. But they will evaluate you on your accuracy of sorting the haystack and needles. Then you just say everything is a hay. You will be 99.99% accurate and you can go home, right? And that's the immediate solution to your really complex optimization problem. So why would you bother to like even search for the good flags? And this is exactly this is exactly what happens every time when you have a like highly unbalanced training set. The minimum that the network finds is a way to keep the accuracy high is to just give the same label to everything and it solved all its problems, right? Because you just want to minimize the loss function and maximize the accuracy. So why not? So now you have to force it to do something else. How are we going to do that? We can just brainstorm just ideas.
I guess you would penalize it a lot more for getting a mistake on a good flag. So you just change your loss function in a way that this penalty reflects what you want.
Mm-hmm. Mm-hmm. That's a good suggestion.
Yeah, you can basically just show it the good flags more often.
Another great suggestion. Perfect. Any more different ideas? Yeah, okay. Yeah,
maybe something like a dropout.
Mm-hmm. Another great suggestions.
Reinforcement learning.
I like. There was someone here. Yeah, there you are. Let me read the Zoom suggestion where Anya is running. Putting different weights. Can you elaborate on that, like in the loss function or initialize the network before the training? But there is indeed a way to do this. Go ahead.
Maybe another suggestion is maybe the accuracy of the model is not the best metric to look at.
Mm-hmm.
Maybe to define some other metric to compare different models.
Mm-hmm. Mm-hmm. Yeah, that's a very overarching contribution and like a very general lesson you should be taking from this. Was there any more raised hands?
I was thinking, I'm not sure whether it makes sense in this case, but maybe you could train in mini batches or of your training set, so such that you have some local representation of your data for different training routine iterations,
mm-hmm.
or also train different models and then average them. That could also be, that should also be less prone to this kind of behavior.
Mm-hmm. Mm-hmm. That's also, oh my God, you are understanding a lot. Then we have another reinforcement learning suggestion. Yeah, so what we did actually here was
there's one last one.
Don't you have these other metrics like precision and recall? Like in, I don't know, I remember seeing them in like manufacturing concepts, like where it's like really important to make sure that certain things are, you have to get it right in some sense, or like cancer detection or any of these cases, and they're using the same metrics that they use in these tasks.
Right. That's true. Right. So this is kind of like a secondary step, that after you train your model and train it properly, only looking at the accuracy is not super meaningful. So there are different statistical tools to do that. I actually, that's a wonderful point. I didn't prepare any slides on these for today, but I will give you a list of resources at the end of the lecture, and I'm specifically going to mention which chapters there mention this stuff if you want to measure things more responsibly. But you were all saying super intelligent things. Basically, you were saying batch engineering in one way or another, that when I am adjusting the way, the network needs to see the data being very balanced. Adjusting the loss function, regularizing responsibly. And it's true that reinforcement learning most probably could solve this task efficiently as well. We didn't do it in this case because it's so hard to get enough training data, and these models are much harder to train than just normal feed forward. So I think that, but in general, it's true. If you would have access to enough data and not just 2 labeling afternoons, then you can probably apply reinforcement learning here with an advantage. But exactly, you guys solved it for yourself. So here in the code, I build up a second model, so you have them saved separately and compare them, and then you get a recipe here. So this is in Keras, but again, it will be similar in other packages. You can just write your own batch generator function that, in our case, created batches that randomly samples fixed number of good training IDs, and then the same fixed number of bad training IDs. So each batch, we show it, has a 50% good flakes represented and 50% bad flakes represented. Of course, then I am showing each good flake relatively often. So it's also another point you made. It's really important to regularize heavily. I don't have it written here, but I think I was using like here is only 40%, but it was between 40 and 60% dropout. Like you just really need to drop half before you reiterate, so you don't start violently overfitting. This training set. Okay, maybe let me then finish this thing. So you create your custom batches, you retrain, and voila, beautiful agreement of the loss function, and beautiful agreement eventually on the accuracy. We have a very small validation set here, so that's why the anomaly at the beginning. But you train until the point where they agree really beautifully, around 75%, because I only gave you a very small training set. So then I load this prediction here, and I see this is a good flake, ends with A, and I am 60% certain. And so it goes. And then you can print the good flakes. And here we will get to the interesting points, that in each figure, it's maybe not so straightforward to think about which one is the good one. So here, the big one is actually not the good one because it's not homogeneous. You want the thickness of your material to be same, because otherwise you cannot layer them very well. You can just think about it as the IKEA furniture kind of situation. So I think that here the good flake actually might be this one, but I am not the one who does it for a living. But exactly like this totally happened, that you will get this output, and you sort of need some kind of expertise to determine which one is the good one. For example, here this big one is a big flake that is a good flake because it's big, well-defined, and homogeneous. And so you could go, and just with a simple fix, you make it work. for the suggestion with the weighting the loss function differently, that's like a super intelligent suggestion that I would always recommend you to entertain. Somehow here we were in such a pathological situation of like a rare data. Then when I did that, it started overfitting much faster on the good flake, on the good flakes than when I actually didn't do this weighting of the wave function. So this is also something, wave function, loss function. We have a question?
Yeah, so I have a, maybe it's just spoiling for for what you're gonna say next, but have you tried class activation mapping on that? This is like interpretability method, which highlights what part of data you look at when making a prediction. So
yeah, no, I didn't, because this was in deep 2018, 2019, but this is exactly what you would nowadays do now when we as a community know about these methods.
Okay.
That's, yeah. Yeah.
So there's another question.
Mm-hmm.
Hi. Hi. So just as a follow-up for this last comment, I think it would be easier to just, when labeling the data, use an inpainting technique, which are like very old and widely used, such that when the cross is marked, the flake that has the cross is painted in red or something like that, and you keep that as a separate mask or something like this.
We were actually looking into this at the beginning, and somehow, yeah, in the end, we managed to compress the data a little bit more, but there is a challenge with this that, okay, let me how to explain it. So the microscope is scanning super much, like each picture is a really big high resolution image. And these are coming like 1 per 2 seconds or something like that. So you are processing a big amount of data really quickly. And then when we were using some of these advanced filtering techniques, like for example, coloring or finding the boundaries, it just was like not scalable in like a data processing time. Because for example, when I got all these terabytes of data, just scanning them with this like super dumb standard deviation condition took like comparably long as actually training the model afterwards. So there was this like kind of speed considerations. At the same time, if you would just care like about not doing it quickly because there is not many groups booking time in the microscope and you could just have run it for 3 days, then this is a totally a thing. This is a totally a thing you would do. But at the same time, you are right, that if you would want to like solve this problem to be like really perfect and industry ready, you can probably do some data compression locally, so the filtering kind of gets quicker through all the data volume or something like that.
And one follow, there is one correlation between the number of trainable parameters and the amount of data set in general. Mm-hmm. And as far as I know, there should be like with 10 more data sets, examples than the trainable parameters. And did you try to have the smaller net, like, yeah, or the same order of parameters and the data sets, and how it works?
Right. So, okay. Here is actually funny, because the parameters that actually specify the data set it's not so easy to actually even quantify them, because I was telling you all this like qualitative thing, right? Like if I would want to write a for loop that identified the right flake, I probably wouldn't do it correctly, but maybe after talking for a week to some expert, we could figure it out. But yeah, with these things, right, this is actually like super essential question, like how do you build these models? Because yesterday I was showing you that I just put like whatever random neurons in the middle, then I throw it at you in the exercise and you optimize it for yourself. But when you are solving like a really hard task, it's not so easy to pick, right? So in this case, I was really building it up layer by layer and filter by filter, and just like starting with pure convolutions, see what they pick up, then understanding what I'm gonna lose with pooling. And really it just grew into this distance, because we wanted to get to the having this in the actual published version, we get to around, I believe, something like 88% accuracy, which is comparable to a PhD student. So this is something that was very important for us.
So if I can follow up on, I think this 10 times larger than number of parameters, this was, maybe I'm wrong, but I believe it's kind of controversial statement right now. So I think it was believed in the 90s, maybe someone may correct me. But now, I mean, if you even take CNN and MNIST when you do as a tutorial, it definitely doesn't meet this 10 times bigger than 10. And so I think it's not longer really true. And this is, yeah, so we can talk about that later.
Interesting. Yeah, thank you, Anna. We have more questions up there. Let's double check the chat on Zoom.
Yeah, sorry. I think this is just like machine learning arrogance speaking, but it seems like this is some task where like you should be able to beat a PhD student pretty easily. And I wanted to know, like, you mentioned like you did like this rotation, scaling and stuff, but like this feature pre-processing thing is actually like really well developed now. Like there are, I don't know, for instance, you can find some really good feature preprocessors on something like Kaggle. Did you try all these methods? And like following up on the neural network point, did you actually try and like borrow some tricks from other neural network architectures which work in similar problems? Like I think anomaly detection is like a pretty well-known problem now, in at least in image classification.
Right. Yeah. So again, this brings me back to the question that we had here with the other filtering methods, right? Like at some point, it's just like it's actually really time exhausting, because like the applying the network is just like under 1 second, right? But doing this on an image, you are going to wait half a minute. And at some point, that's just like it's just like not like super scalable, because they are not like I will continue explaining to this. You want to have a sort of continuous workflow, because then you want the microscope to go back and actually zoom on the flag that is the identified one, and then someone actually comes and pick it up, right? So it's kind of, you don't want to have this like 1 hour lag because you are building some kind of super sophisticated like filtering architecture. But at the same time, like I agree, like if this would be like a 3-year problem that it's really worth to think about it seriously, you would probably do something like this. But there is a lot of like interplay that goes into that. And yeah, again, about the anomaly detection, it's again, this is the example where I am explaining you how to apply supervised network. We do and are applying anomaly detection method in another context, but that's not what we did in this lecture, right? Like,
I think this feature engineering is actually pretty light by now, because you don't even get, I don't know, maybe we talk later.
Yeah, I think that's better, right? Like let's have a conversation, but like also, I mean, let's have a conversation that is not, why didn't you do this, right? Like this is a simple example that I want to explain you something, and then we can discuss the filtering afterwards. But right, but either way, like what I kind of, okay, so first thing, what really you need to take from this is really just this meme, right? Like you cannot like take some random training set, have a network that is like 99% accurate, and then be super happy about it, and you are done, right? So, and through yesterday till today, we were talking about all of these different things that you can print from looking at the weights to check for overfitting, to kind of really understand like what's happening, and trying to like, for example, create super small test set where you understand each example and then you apply the network. That's a really good strategy to understand what it is that it got wrong specifically. And then I see that you have a lot of funds here of advanced filtering, and that's what you can like problem specific, you can do and develop and use any of these packages. The message here from my side wanted to be that even with a simple pre-processing technique, you can actually achieve really a lot right? Because you don't need to be an expert and be intimidated that you don't understand how this like boundary search algorithm works. Like you can really just think like a physicist and think about what I need to check for if I load the data. And just the simple things like a standard deviation or a appearance of a certain color regime, or each data is going to be different, or just some appearance of some type of peak, you can just make like a super trivial filtering method for yourself, and it's not going to compete very well with like a state of art other filtering methods, but it's a good enough to solve a problem like this, right? So then the whole process works something like this. The microscope is moving, and at each position, it takes a picture like this one. Then we run the pre-processing algorithm, which in our case was this standard deviation filter and this cutting out of the windows, because another thing you need to think about, it's sort of a standardization of your training set. Fun fact, as the microscope is moving and taking these pictures, they actually don't always have the same size in terms of pixels. So there is a lot of kind of things that is maybe hidden under this, or it's not in the terms of pixels, but it's not the same in terms of the like actual size on the wafer. Like it fluctuates a little bit. So by just a simple trick like this, by cutting out the squares of the same pixel size that is chosen intelligently, you just create a training set that is like super uniform. Then you build a classifier, which in our case grew up to be this like very deep convolutional network with a lot of filters. And then again, you need to, it's not the end, right? Because it's not the fact that my computer here tells me this is a good flake, that's not. So I also need to write a script to tell me where is the good flake in the square, where is the square on the picture, and then where is the picture on the wafer. And then you can sort of go back, and then I have in the red all the squares that the algorithm identified for this specific image. And so, for example, you see that it found this big flag, but it only found the top. It only found the top corner. But if you go, then what the microscope does is that it gets told these coordinates, so it goes there and zooms at it, and you can pick up the flake if you want it. So basically what happened in the case of this hexagonal boron nitride with this kind of really like crude disadvantage from the point of view of the good data sample workflow, for each 10,000 flakes that came in, we identified 200 candidates, and out of the 200 candidates, a person that then afterwards said that about 100 is good. And then you asked me, okay, but then perhaps you should have used a better filtering because this sucks. How is it that like only 50% on this narrowed down set is useful? So maybe I will come back to this later. Let me first show this. So why is this is why? And this brings us back to this question that we had from Zoom. These are the 3 leading experts of ETH Zurich in flake labeling. And on this 25 flakes, you see how well do they agree. So this is a problem, right? Because even if you are a super advanced expert, you are doing a specific experiment, and what you want from the flake may differ. And this comes back to your question about that the criterion was label everything that's useful. So you have some really, really beautiful flakes like this one, where everyone agrees. But then you have a flakes like this one, where probably they wanted this one, but then the third person said, this is too close to corner to the wafer for me to bother about. And these are this kind of criteria that are kind of personal, but they are going to come into this one way or another if you are going to have a human operator labeling flakes. And I cannot dump all the flakes that have one person. We have a question over here. That you have a one person telling me that maybe that's not so good because finding a good flake was so rare at the beginning.
I just wanted to know if you like took each of these pictures, or if you had like a veto system, like if there's one red cross, then it's a red cross for everyone basically, or something like that, or if you had the same data with multiple labels.
No, we just, because exactly what I just explained, if one person said it's good, then I take it. Then I take it as good because it's so hard to find the good ones, basically. So then it leads to this classification errors, so to speak, later on. Yeah. But again, if you would have access to more data, you would do exact opposite, right? You would pick for the training only the ones that have a popular agreement or some thresholds. So,
Thanks. So, who evaluated the final results? Were these these three humans too? Because it could be that the neural network did everything right, just evaluating the results of the neural network afterwards. If it would be done the same way as this, then the last evaluation could be the wrong one and not the neural network.
right. So yeah, so this was just like this super specific subset with this specific control group, but actually the labeling of the flakes was really this huge undertaking because you need to look at so much data before you find a good one. So we actually had super many people labeling, a whole group. I think we had up to, I want to say 15 people were labeling at some point, maybe even more. And for the evaluation, again, I just send them the data and then I ask whoever is at hand to tell me what is the percentage of the good ones. So you are completely right that the percentage that at least one person would find to be good, but wasn't in the lab that day is probably higher than what we were getting back. So this 50% estimate is just super conservative averaged one. So we wouldn't also not exaggerate it on the opinion of one person.
So I don't know if everyone is aware, but neural networks are robust against massive label noise. So it's in some cases you can have 10 times as many randomly labeled examples as correctly labeled examples in your data set, and you still would achieve almost the same prediction accuracy.
Mm-hmm.
So I think this is important to understand here. Thanks.
Yeah, that's a great point. Thank you for bringing that up. For us, the final evaluation was also the sort of biased human evaluation. So we would have have someone to actually say this is working for this many flakes. Go ahead, please.
So my question is the following. So you have many students labeling the flakes, and then would it be a possibility that, for instance, instead of choosing the labels that had the highest agreement, you take the average? So there is a continuous variable that labels the possibility, the probability, or the quality of the flake, and then the machine learning algorithm would also, instead of binary labeling, it would provide us with a continuous number which would reflect the degree to which we are confident in the flake. Would it be feasible, possible, or is it too complex?
Right, again, theoretically, this is perfectly feasible. When you are working with this practical context, it just doesn't I am not going to come to the lab and make a case that they should all labeled samples after each other. So we really have, once one person labels something, it's labeled. And then we move on to it's just, I already need to, just in terms of money and human labor, I need to case for myself to allocate for a big lab a lot. And allocated triple is not an option. And this is just like a very practical constraint. So what you are proposing is like exactly theoretically correct thing to do to sort of analyze this set and also understand what kind of biases are there, like the thing that Sebastian was just mentioning, but it wasn't feasible for this specific project, and often it isn't, because, for example, sometimes you get a good sample, you measure it once, and then when the fridge is warm, you are not going to cool down again and find the good qubits again. So this is very sensitive, and sometimes you just have the data that you have.
And this is a good idea to use different data sets, labeled, but for example, group of 5 people, like you have 5 people make this labeling, this and this, and make like the prediction, like the ensemble prediction on 3 different neural networks. And it can be like the beneficial or rather not for this particular case.
This is perfect segue to my next point, because actually this is what we did. Like, there is basically, because you are looking at like so many flakes, and you really want to what you want to in the end optimize is also the number that the expert has to look at. Because if I get a 10,000 flakes and I still have to tell someone you have to look at 2,000 afterwards and evaluate which is the one you want, I didn't save them very much time. So we trained 3 different models on the same training set, because again, limited data. If this wasn't the case, I am sure you can come up for me with many examples. How would you do this differently? We train these models and we apply them consecutively. I take the first model, and this is just like on a very small sample, so we could really check how it shrinks, and we have actually labeled the control, like a control labeled how many good flakes is there. I apply it on about 1,000 flakes, out of which 100 is good. It spits out 224, out of which 98 is labeled as good. Then I put it into the next network, and it goes from 98 good to 87 good, but it lowers the total number of flakes experimentalist has to look at to 160. And the 3 models goes to 150 and 86 flakes. So we get like this, we get into the regime that really every second one you look at is a good one. And then again, there is this exchange rate that at some point you could keep training more models and applying them, but you don't want to lose too many good flakes and so on. So we chose 3 models here. And basically you just start by initializing the weights differently. And because you do a lot of dropouts, it's not deterministic on a fixed training set, so basically if the flake is on let's say it's a good flake, and one model would determine it with a 51% probability as bad, it may very well be that if you retrain it, the next one only find it 49% probability bad, and it will sway it into the good camp and so on. So or more likely, what you see happening here is that what actually happened is that applying multiple models, you weed out the bad flakes that the model almost thought that they would be good. So this kind of ensemble way of doing it is a way to sort of get rid of the false positive. Okay, so then this whole thing was like super painful, right? Because you needed to collect all these flakes, you need all these days and human labor to label them. So when we were then applying it on different materials, we tried something that is a super useful thing that I want you to know about. So you don't start building some model from scratch and accumulating horrible amount of training data. If you could take an existing model and retrain it. There is a lot of generic network. There is like a big, you may know about an ImageNet, which is an object recognition network. So if you want to build a neural network that recognizes a specific thing, it could be a good idea to load that and then retrain it and not start from scratch. And this is what we did here. We went to all of this horrible thing with the HBN. So then when we got the graphite flakes, we just retrained the whole network on only 200 of a good flakes. And it works. After doing these 3 models, the same method as before, I get into the regime that every second flake is useful to a experimentalist in that group. So this is good, right? Because they only had to collect super little. So, and then the hard thing comes, which is the bilayer graphene. So that's super hard to see under the microscope. The bilayer graphene flakes are the ones that you almost cannot see because they are light blue. They are almost transparent. And here you have also the examples of the 2 different lightnings, actually 3 different lightnings of the microscope. And here you have a bilayer graphene flake around here, but you almost cannot see it with the naked eye. So then there is also a secondary issue that for a lot of these pictures, even if you are sitting there an expert looking at the microscope, you cannot find it super well. So here they only could find the 40 good graphene flakes for us to retrain the model. And what we end up with was that it spits about 250 flakes and 26 of the 260 flakes and 26 of them is good. So that's 10%, but it's still better than looking at 4,000 flakes and trying to find the 20 good ones, right? So this ratio between what the model gives you, this is what you should look at, and what out of that, what's actually useful, it keeps widening. But I think in this case, it's really a consequence of not getting enough of experimental data. And yeah, I was leaving ETH after that, so I didn't stay around long enough to keep accumulating flakes and retrain it, but they are using this model for other materials, so I hope this will come to fruition at some point. Let me finish this part with a video of how it actually works. So this is in real time. This is the microscope already zooming on the flakes that it thinks into the coordinates that it thinks it's good. So the switch between the flake is the time that it takes, and this is already the zooming, and it's like you should look at this one. You should look at which one here? I don't know. Here you should look at this one probably. Here you should look at this one here, and so on. And so it goes. And you see that sometimes it still messes up because this one was completely out of focus. But basically you can just do these things at this speed. Again, this just look at this meme, and this is what I want you to know from this lecture, because just balanced training sets always and smart preprocessing. Let's take a break.
Sorry, one thing, we are not allowed to bring coffee here or anything except water. Water is probably okay. Yes, exactly. And the second announcement is that please, the last person or people who come to the office to the hall after lecture starts, always to close the door, because then we hear the voices, right? What's to hear them?
Hi, welcome back. So I have a second example for you of such a machine learning experimental control, but we only have a half an hour or so left. So let's see how far we are going to get. Maybe I will try to be a little bit quicker explaining it, but like as before, just like ask me questions anytime, because it's better to make this conversational and make you understand than me just skipping something and talking at you. Okay, who knows what is a quantum dot? Okay, so let's have someone explain it.
So a quantum dot is just a one-dimensional quantum thing in a material, basically. So, for example, an atom or something that is like different from the atoms around it, like it's just supposed to be like we had 2D materials before. Or a quantum dot is basically zero-dimensional, not one-dimensional.
Yeah, that's a good explanation. So you may know that quantum dots are one of these candidates for quantum computing. I think some of you here have some quantum information background. I am interested to hear, like, let's have a quick conversation about like, what are like, I don't want to call it advantages or disadvantages, but maybe like a features of quantum dots as a computing platform compared to some others. Anyone would like to chip in for this? I saw lots of raised hands about knowing about quantum dots, so I am sure you can.
They have discrete states due to confinement of the carriers.
That's true. That's true. And they are super scalable, right? Because we just said it can be like just one electron that is really confined in all the spatial dimensions. So what's stopping me from making a tiny quantum processor with 1 million of such qubits and be done with building quantum computers?
First of all, it's hard to make them interact, and second of all, when you fabricate them, they're all very different, so they're not indistinguishable.
Right. Yeah, that's exactly going into the correct direction. When you are building these semiconductor devices and you are really trying to confine an electron in the material that is made of electrons. So you always kind of live in like a cloud of mass and this many body interactions that are happening around you. So here is the picture of a quantum dot. This is the green thing schematically here. The gray things are gates that confine it. And then one way to measure them is to have a second electrode and then measure the current that passes through here to here. This is called a quantum point contact. And how it works, it's just the Coulomb thing that you know from your electromagnetic classes, right? Like if there is an electron sitting here, you can register it with the extra electrode just because of the current going through here will be different if there is an electron sitting here or not. So this is how you detect not the whole quantum state, but at least the presence and absence of the electron. So this is an example from the electron microscope of how such quantum dots look in real life. Here are 3 next to each other. And then you have all these gates that are controlling them. And this is the quantum point contact that I was just showing you schematically. So one thing that people are interested in, so you have these quantum dots and you want to create quantum states from them. A simple computational basis you can think about is just an occupational basis. That, for example, you will have 2 quantum dots and there will be state that has a 0 electron in one and 1 electron in the other dot. And then you can do, this is a state on which you can do some quantum gate and so on and so forth. So you want to prepare this occupational computational states that are really just based on how many electrons is in each dot. However, this is kind of an annoying task because of all this noise and like level of control that you have in general in these semiconductor systems. So basically what you need to do is to find the current that goes into your control gates that allows you to have the occupation in the dots that you want and that lets you prepare such quantum state. This is a so-called charge stability diagram where on the axis you have a voltages on 2 selected gates. And the color scale is a derivative of the current that is going through the quantum point contact. And basically, every time the current changes a lot, you have a charge transition in the dot. So if I start from this state, and I have a 1 transition here, I move to the state that there is a 1 electron on the left and 0 electron on the right. If I move 1 up, I am going to move to the state 1 electron on the left, 1 electrons on the right. If I would go to this one, it would be 2 electrons on the left, 1 electron on the right, and so on and so forth. Now, if I would just pick a random square here, I am pretty sure you can counting like that figure out what is the state. Let's actually pick an easier one. Tell me what is the state in this square-ish here. There is a comment from. So these are, sorry, yeah, see, I am going fast. Thank you for the question. So the question is, what are the PG1 and PG2? Those are the so-called plunger gates. It's a one of these gates, of the gates that we have. Those are the gates that control the occupation specifically. So PG1 is here and PG2 is here, and we are looking at these two quantum dots. And it's really like, don't worry so much about these names of the gates. Just think about it. This is a plot with two gates, and on one axis is the voltage on the gate 1, and on the second axis is the voltage on the gate 2, and color is the derivative of the current. Okay, this feels like this was understood. Let's go back to this. Was it somehow not clear? Let me then ask an easier question. What about this one? Perfect, thank you.
0, 2.
Perfect, and then this one would be?
0, 3.
Thank you, right. Just because it's simple, just don't worry and answer it anyhow, so everyone knows what we are talking about, right? So, if you would have this super finely measured charge stability diagram when everything worked out perfectly, or the other voltages that you don't see in this plot are adjusted correctly, you can just go point on the separate, these are called the so-called Coulomb diamonds, and just pick your charge state and be done with it. Except that for the state preparation in quantum physics, this is not super practical method, because it takes forever to measure all of these points at the sufficient resolution such that you can just like look at it and adjust the voltage. And maybe by the time you figure it out, something has changed, because again, like a dirty semiconductor many-body system, something has fluctuated somewhere and it will be shifted anyhow. So what we did in this project, again, like a purpose here is to not find like the most optimal, beautiful theoretical method, but being in a situation, we have a sample in the fridge, we can measure it next week, so let's just fix it. We were trying to find a method to do this. This is the sort of a task of tuning when you find a specific quantum state, and the field that people do this automatically is called auto-tuning. And this is what we wanted to do here. Again, instead of a PhD students turning knobs on all the voltages of all these gates, then finding what are the conditions to measure this one charge stability diagram, measure all of the points that you see here, and then figure out what is the voltage to go to the correct state. We want to find really, really streamlined method to do this. And again, this is a perfect opportunity for a convolutional neural network, where what we did is that we measured very, very small patches of this charge stability diagram with a very rough resolution. I'm going to show you in a second. Then we classified the content of those squares. Basically, you have like three options here, right? Like either you have a line going this way, so that means that you can shift the state in the left dot, or you have a line that is going this way, which means that you can shift the state in the right dot. And then you have a line that goes both ways, which means that there is a transition contained in the patch, like you see here, boop, boop, between two neighboring dots. So basically, what you need to figure out is like how many transitions you have here and how you move to the state from there that you want. And I am going to explain exactly how this works in a second. This is again one of those cases where how specifically the charge stability diagrams look, that's super experiment specific. So we actually labeled actual experimental data here. We measured a full 128 of charge stability diagrams like this one. And then we introduced some augmentations. It's again what we were discussing previously with rotating and mirroring the flakes. Here, Renato, my student, just wrote a script to sort of do it manually to introduce other angles for which the charge transitions should go. But again, I am sure you could come up with like a more sophisticated data processing techniques to do it. Then from this, we extracted 600,000 patches, but to avoid errors, we labeled them with 3 labels that we label each corner. So for example, this corner, I would label with the label that tells me there is a transition in the left dot. This corner, I would label with the label that tells me there is a transition both in the right dot and the left dot. And this one would have a label transition in the right dot only. Are you following this? Okay, I see nodding. So you see that this is, of course, informationally redundant as hell. But the problem is that when I show you more images, you will see it's not so easy to tell when you have a transition or not. So we do this super informationally redundant thing where we classify each corner. And each corner has basically 4 options that either there is no transition, transition in the left dot, transition in the right dot, and transition in both. And that's the classification probability distribution we are looking at. And then you can just train feed-forward convolutional neural network that gives you around 99% accuracy per patch. And then how it works in practice. Because we are only looking at the small subsets of this charge stability diagram, we need to develop some workflow, because if I am here in the middle of nowhere, nothing tells me that there has been 3 lines before this patch and 4 lines below it, right? So it's very isolated amount of information. So what we do is that first we find a 0-0 state that you keep finding lines and you keep shifting. If you find both transition line, you keep shifting diagonally down to 0. If you find only this one, you keep going that way. If you find only this one, you keep going that way. And this is just like a hard-coded algorithmic feedback loop that you introduce just from understanding how this charge stability diagram works. And when you don't have any more lines like that, you can then systematically start moving into the state you want. So here I say, I want a state 3-2. I know that I'm in 0-0, so I will keep shift diagonally, measure very small patch, classify how many lines I shift and move, and so on. This is how it works. This is the on-device tuning runs for the preparation of the 2-1 state. And here you have 2 successful examples of how you can get there. Here, I want to draw your attention to how the measurement actually grainily looks here. It's actually not super simple to know, like, where are the transitions exactly, right? Like, for example, this one is very nicely visible, but in this region it's not so nice. Like, but we basically decrease the amount of measurement data by order of magnitude per patch doing it like this. And because we were measuring just this very small subset, it was actually much more in total, because nobody has to measure the whole charge stability diagram and then literally count the transitions and finding the voltage. So this is then how it works. And then again, you can do this very, very automatically, because you only need to have the classification that tells you how many lines you have. And then you just need to have a feedback loop that connects the output of your classification to your voltages. And you just keep playing this game of shifting the voltages, measuring a little bit and classifying. And then you can prepare states like this fully automatically. And again, this is kind of like a valuable contribution to the experimental workflow because you don't want to sit there and just like tune the knob until you see the voltage that you were looking for. So we have a question.
Hi, I'm not sure I'm properly understanding how you found the 0, 0, because I thought it was when you didn't find lines, but here in the experimental images you were showing, there's still like blue lines around it, no? Or, well, at least it seems like it.
Yeah, so because you need to, right? So you have like the values of the currents kind of fluctuate, but really like a true existing blue line is this one that gets you to the 0, 1.
Oh, okay.
So like a technical thing to say is that for the finding the 0, 0, the patches we were measuring were really bigger and rough than the one I am showing you on the fine tuning. And then you get into the, so it's not just like, yeah, it's about like what it has to learn to classify is to distinguish what's actually a line in the picture and what's actually just some noise in the data. But this is really just a fluctuation. It's not a charge transition. Only charge transition is this one. And basically what we did is that we found a really big square over here without any lines. And then we just went into the northeast corner. And that's the point from which we start this more divided tuning.
Okay. Thank you.
Thanks. Now this has a problem. This has a challenge because while each of these classifiers actually work with a really high probability, like something like 98%, it becomes a problem when you have a 98% probability on the first patch and then you multiply it with the 98 on the second patch and 98 at the third. So after all of this, you actually end up with something like 60% success for the fine tuning. So in practice, you need to run it a couple of times before it goes into the correct state. This is a confusion matrix. This is like what we saw with the unsupervised learning yesterday was like a continuous version of this. Like this just tells you the correct occupation versus predicted occupation. So what you want is to have all the numbers on the diagonal, but you don't because, for example, it thinks that the occupation 2, 3 was 2, 2 because it missed the line. So the errors comes exactly from that this like very grained measurement sometimes misses the line. But again, 60% success compared to the PhD student, it's a good trade-off, let's say. Like so it's a beginning. So it's a beginning of something, and hopefully with more sophisticated methods, you can also do better here. There is a natural question that you are going to ask me, that is, Eliška, why didn't you use the reinforcement learning here? Why didn't I? Maybe that would be better, no? Any ideas? So what you were supposed to learn from the first half of the lecture is that not just always about a question of like what's theoretically more suitable, there are other considerations. So if I told you here how I prepared the data. So
well, I guess the PhDs were in the end happier with this 60% result than having to label a lot more data at the beginning to have a proper data set for the reinforcement learning.
Yeah, that's exactly the great point, right? Like, and there are actually other groups that like labeled more intensively, and for the different tasks related to this tuning, they are doing reinforcement learning because it's the right thing to do, right? Because you don't want to multiply these probabilities from a multiple consecutive model. You want to have a one model that interactively adapts, but having enough data to actually train the reinforcement learning is a practical obstacle. So this can be a kind of a lesson that like if you don't, then you can still make it work well enough with the just like feed-forward models. And this is really important to become this creative when you actually start working with the experimental data, because the theoretical proposals with machine learning models, they often assumes like amount of data for the training and validation that is just like experimentally like completely unfeasible. Yeah, so there are other things that I wanted to mention, just like the other people adapting these ideas and finding like a cool ways to speed it up or get around a different problem. There is a paper from the team of Justina Zvolák in NIST where they do this, but they just, instead of measuring the whole patch, they only measure arrays until they find the boundary of the charge stability square, because not all points in this diagrams are equally meaningful, right? Like what I really just want to know is this, and all this pink stuff we measured here, that's useless. So this kind of ray-based boundary detection method can be really quick way to just measure the lines until you hit the charge transition in a few points, and then you can extrapolate where it went, and you can measure even less. So then Justina like decreased the data demands for this kind of methods by like another 60%. And then you can also play the game of, I was just showing you very schematically what kind of neural network we used here, but you can play the game of minimizing these networks, because what's a really essential frontier for this kind of research is this. You don't actually want to run a sophisticated algorithm on a computer that sits next to your device. This is also why neural networks are super cool, because once the trained model, it's just like a simple algebra operation when you are applying it on a new data. So you can encode it on the FPGA or another controller. You can encode it directly on your experiment, right? Because this overhead of reading out the data, then initializing the model in Python, seeing what it does, and then going through all the cabling like back to the experiment, that's super inefficient, and it's never going to scale as the quantum devices are scaling. So the important frontier to solve is to actually build a super minimal models that can be encoded on actual control software for an actual experiment and do not require a 50 Python packages installation on a Windows computer next to it, right? So Okay, so the question is, could the angles of the intersections be increasing, decreasing as you increase the voltages, so you could use it and predicts where you are without going to 0, 0 first? Or most of the blue line intersections are equivalent and indistinguishable? You're right. So the angles are changing a little bit, but mainly they are super specific, like the starting angle is kind of specific to each experiment. So it could sort of happen that if you just fix the angle, you would think that you are on third line transition for one experiment, but for another double quantum dot, you will be at the fifth line or something like that. So making absolute criteria like that is dangerous, but you could go for some intelligent implementation of this ray method to kind of compare few against each other. But like, again, this data is so noisy that you cannot just say it's 30 degrees and that's what I'm going to use. Because if this was the case, there would be like infinite algorithmic techniques that could just do this and you would be done. But because it's not, it's machine learning is really meaningful. Yeah, here I was just mentioning then this paper that does amazing job as using this method, but miniaturizing the neural network such that they have like really handful of neurons. So once it's trained, the matrix matrices you have that store the model are really, really small. So it wouldn't be hard to encode it into an actual experiment, let's say. We are running out of time. I am going to skip this. I also wanted to do interactive exercise here, but we don't have time. But I just want to, before we finish, I just want to wrap up with you telling me what you have learned. So now you will not have a discussion groups to figure it out, but I hope we can make it work anyways. So there were two super important messages, like what are some important practices for doing this basic workflow in machine learning, and what are the important properties of the physics problem such that machine learning is a solution to it and not just like proof of principle of using machine learning. Okay, so for the first question, what are some important practices in machine learning for data preparation? Can someone give me example of the practice that you learned by talking to me for the last 2 days? So I know you're hungry for lunch, but this we have to get through because I need to go home like satisfied that I didn't talk into the wall for 6 hours. Please go ahead.
Batch normalization, data centralization, and yeah.
Okay, yeah, those are great examples of really just having a well-balanced, reasonable data where all the things you want to see are represented in some way, and balancing your training batches is really key. So that's a good example. Okay, let's stick with one. So I am not going too much over time. The next one, some important practices for building neural networks or machine learning models in general.
Yeah, and make use of your correlations in your data, like with the local, if they're locally correlated, use convolutions and make sure that you don't overfit by using dropouts. And another thing I learned is machine learning and memes are a good combination.
Yeah. Okay. Yeah. That was a great summary. We have a follow-up comment here.
I also think try the easiest and simplest model first.
Yeah. Yeah. That's important. You should never start with a 10-layer convolutional network as your first try, right? Go ahead.
It's more of a question. Is there a heuristic on the number of parameters you need for a given problem? I mean,
it's a bit what Anya was discussing. There is always this there is like these guidelines, but that keep changing as the field is developing. If I would have to get when I was starting this and I didn't know anything and I was a PhD student, I would just look at the problem that worked, for example, MNIST classification, and I looked like, so in MNIST data set, I have like 5,000 examples per class. In my data set, I have maybe like 2 examples per parameter estimation I want to learn. So that's probably not going to work. So I am always building, like I take some minimal model that does the thing that I want to achieve. And I kind of look at like ratios of the different properties of that thing. And that I think that extrapolates as a good, like very like 0, starting point. And then you can sort of start iterating from there. If anyone has a different follow-up on it, feel free. But to my knowledge, there is not really rigorous recipe that would tell you this. We have a raised hand over there.
I mean, just a quick follow-up. There is no like recipe for that as far as I know in the machine learning community, but the only thing that you can rely on is the outcome phrasers. So basically this means that the lower you can go with your parameters, the easiest model you can make, it tends to always be the best you could have.
Okay, one thing that I want to add there, I don't know like how controversial this is, but something that I heard is that often it's a good idea to rather build a bigger model and then just regularize it down, because often gives very good results as well. And I think this is also a good experience.
Well, if you're called Google and you have indefinite power, that's probably the good approach. But if you are like a small group with limited amount of computing power, then it's probably, I mean, of course that could work, but it might not be ideal.
Yeah, I like this discussion a lot. When you are starting to practicing this as a student at the universities, you are going to run into queuing at the university cluster. So you want to estimate your resources very, very, very well. And just like learning on how to benchmark these models during training, so you are not rerunning 3-day training over and over again just to find the hyperparameters, that will be a thing, right? But like exactly this point, right? Like if I have infinite resources, I just go with the bigger model and it works. But sometimes, especially with the sophisticated methods that you are going to hear later on with this course, it's training a recurrent network, training an RL, it's not a cheap thing, GPU time, CPU time wise. Do we have any more comments here? Okay, then maybe let me just skip to the final question, because that's the really, really important one. So what are the important properties of the physics problem that actually call for a machine learning solution, right? You should leave the school writing papers when you solve a new problems with a meaningful computational method. You shouldn't write papers that like, I applied machine learning to this and it makes sense because nobody before applied machine learning to it, even though there is an analytical solution, but look, right? So finding this, like what it is about a problem that what we are teaching you here actually makes sense to use it. Can we figure out how to summarize this to finish this off? I think we talked about it, right, yesterday at the beginning of the first lecture. Can anyone remember some points that characterize problems that machine learning makes it meaningful? We have a gray hoodie here.
Yeah, I mean, the curse of dimensionality of quantum many-body systems is what we set as a main point. So neural networks can help to like compress the information into few parameters.
Okay, so that's one great point. The problem is too big that just finding a clean analytical solution doesn't work. So it's kind of variational approach. Perfect, thank you. I want to hear at least a second one before we go. I see someone over there.
Not exactly a second point. I just wanted to say that the high dimensionality of the problem. So in high dimensions, usual, like, I don't know, polynomials, they have this curse of dimensionality, and it looks from machine learning community, like image processing, it looks that neural networks are really good in approximating high dimensional functions. So it's not about compressing, but it's about like representing high dimensional functions efficiently. So that's my point, which is not the second.
Okay, sure. Yeah, maybe let's not get into discourse between compressing and representation right now, but good point. Yes, we can discuss afterwards. I want to hear one more thing. We have someone here in a red hoodie.
Well, I would say that one of the most important things is that you have data, like reasonable amount of data, either experimental or that you can simulate, because otherwise machine learning won't work. And also that there is not, say, an easy solution or an easy algorithm, and either analytical or numerical, then you could apply, because otherwise you're just doing machine learning for the sake of it.
That's great. That's great. Do we know about an example of the algorithm? What it is? What makes it such that there is no simple algorithm that solves the thing? Can we, maybe I didn't say that explicitly enough yesterday, like what it is that like, okay, so this will be not very quantum information oriented example and not chemistry one, but like what it is about having a quantum processor that I am measuring, and sometimes it's a small one, it's just a 7 qubits, but The experimentalists tell you your stupid theoretical prediction with the perfect Rabi oscillation here doesn't apply at all, like because of something. What is that something? So what is it different about like an experimentally real quantum device? You have someone in the orange hoodie there, and your theoretical model of it.
Oh, so there was somebody else? No, so maybe I will give way to the younger students. Well, so I would say that maybe two things. One is that the complexity of the system, so that individual parts that compose the entire system are very different, slightly different from one another. So a simple theory cannot really you cannot really simplify simplify it as an analytical model. And the other thing is that there is always an inherent noise in data that we gather, and yeah, that is also
exactly
an important factor.
Exactly, perfect. Thank you so much. This was all of your points. Excellent. And this last point, just because it took a while to get there, like even if I am going to make an experiment where I'm just like throwing ball in the air and I am going to use the Newton law to do the predictions, it's not going to be the same, right? Because how do I account for like air resistivity exactly in the different weather conditions? And that's like such a stupid example from your high school physics. Now think about what kind of complex noise arises on a quantum processor and different like long range correlations and correlated noise and all of these things. So we can have these simple models that like generate the data, but the real data that you get from the experiments, they are oftentimes they have features that are not explainable or related to the theoretical model, and that's why this is the thing where I don't know. Then the data-driven technique, machine learning, or another one can be used. Okay, so thank you. This was very cool. This was very cool summary. I want to finish by showing you links to some exciting resources online that I used to prepare these lectures, but I also used when I was first learning these things. Phi Lee in Stanford it's a purely computational CS class. So, you know, it's not super related to physics, but if you really just you didn't understand exactly how the convolution filters work, just go there and read everything about that. Florian Marquardt has also machine learning for physicists website. I and some colleagues has written a book also about machine learning in context of sciences, which is also freely available online. Michael Nielsen also has a super cool book, which is also more on a CS side of like a deep learning theory. And I think if you are just starting out, and I know many of you already but best thing is to just pick a simple problem in your PhD, in your research field. It doesn't have to be ambitious paper problem, but just pick a simple problem of something that interests you and do it. And once you do 2 or 3, you are going to be super proficient with this method. And with that, I am done with all my lectures. Thanks a lot for listening and participating. And yeah, I'm staying around until Friday if you wanna chat. Thank you.
So not really a closing question, just thank you really much, Eliška. Like I really enjoyed your lectures very much, and I talked with a lot of other people who really enjoyed your lectures very much. Thank you. This was really amazing.
Oh, thank you. Thank you so much. And thanks so much all for participating. This was my first lecturing after lecturing after a long break. And it's a very different experience than just talking at you on Zoom. So I'm also looking forward to have more conversations with you for the rest of the week.
Okay, so if there are no more questions, let's thank Eliška once more for fantastic series of lectures.